Welcome, and thank you for joining. Today, we'll explore an exciting problem from LeetCode, number 973, titled K Closest Points to Origin. This is a popular algorithm problem that tests your ability to work with geometric concepts and efficient sorting techniques. Let's dive into the details and analyze the best approaches to solve it. This problem is about finding the closest points to the origin on a 2D plane. You are given an array of points, where each point is represented as a pair of coordinates, x, y. Additionally, you are given an integer k, which specifies how many of the closest points you need to return. The task is to return the k closest points to the origin. The order of the points in the output doesn't matter, and the problem guarantees that all distances will be unique, so you won't have to worry about ties between points. The input includes the list of points and the integer k, while the output will be a list of k points with the smallest distances from the origin. The distance we are considering here is the Euclidean distance, calculated as x2 plus y2, but without taking the square root for simplicity. Let's examine an example to clarify the problem further. Suppose the input points are 1, 3, 2, 2, and k is 1. Here, we need to return the single closest point to the origin. First, calculate the distance of each point. The distance of 1, 3 is 1/2 plus 3 squared equals 10, and the distance of -2, 2 is -2/2 plus 2 squared equals 8. Since k equals 1, we return the point with the smallest distance, which is -2, 2. This demonstrates how we determine the closest point based on the Euclidean distance. In this case, the output is -2, 2. Now, consider another example with input points 3, 3, 5, -1, -2, 4, and k equals 2. Here, we need to return the 2 points closest to the origin. Calculate the distances. 3, 3 has a distance of 3/2 plus 3 squared equals 18, 5, -1 has a distance of 5/2 plus -1/2 equals 26, and -2, 4 has a distance of -2/2 plus 4 squared equals 20. Among these, the two smallest distances are 18 and 20, corresponding to the points 3, 3, and -2, 4. Therefore, the output is 3, 3, -2, 4. This illustrates how to select the closest k points by comparing their distances. Finally, let's look at one more example with input points 0, 1, 1, 0, and k equals 2. Since k equals the total number of points, we need to return both points. Calculate the distances. 0, 1 has a distance of 0/2 plus 1 squared equals 1, and 1, 0 has a distance of 1/2 plus 0 squared equals 1. Both points are equidistant from the origin, so we include both in the output. The result is 0, 1, 1, 0. In terms of constraints, the problem ensures that 1 equals k equals points.length equals 10/4 and that coordinates can be as large as -10/4 to 10/4. It's also important to handle edge cases, such as when k equals the number of points, when distances are tied, or when inputs approach the maximum size limit. Efficient algorithms are crucial to handle these larger cases effectively. To solve the problem of finding the k closest points to the origin, we can consider a few different approaches. First, the brute force approach is straightforward and intuitive. Here, we calculate the Euclidean distance for every point from the origin. Remember, we can skip taking the square root to save computation since comparing squared distances is sufficient. Once we have all the distances, we sort the points in ascending order based on these values and return the first k points from the sorted list. While this method is easy to implement, it has a time complexity of n log n due to the sorting step, which can become inefficient for large datasets. Additionally, it requires n space for storing the distances. The main drawback is that sorting the entire list is unnecessary when we only need the top k closest points. Next, we have an optimized approach using a max heap. Here, instead of sorting all the points, we maintain a heap of size k to keep track of the closest points dynamically. The heap helps us efficiently discard points that are farther away as we iterate through the list. By focusing only on k elements, this method reduces unnecessary computations and improves efficiency. The time complexity here is n log k, where n is the total number of points, and k is the size of the heap. This makes it significantly better than the brute force approach for larger datasets. The space complexity of the heap-based approach is O(k), as we only store k elements in the heap at any given time. This makes it memory efficient for smaller k values. However, it does require additional space for the heap structure itself, which is an important trade-off to consider. Another alternative is the quick select algorithm, which is inspired by quicksort. Quick select partitions the points based on a randomly chosen pivot, separating them into groups of points closer or farther than the pivot. The key advantage here is that we don't need to sort the entire list. Instead, by focusing on the partition containing the k closest points, we can narrow down the search space efficiently. If the pivot index matches k, we stop and return the closest k points. Otherwise, we recursively process the relevant partition. This approach has an average time complexity of O(n), making it the fastest option in most cases. However, its worst-case time complexity is O(n²), which occurs when the pivot selection is poor. Quick select is also memory efficient with an O(1) space complexity since the partitioning is done in place. While it's the most efficient in terms of average time complexity, the potential for poor pivot selection and the added complexity of implementation are significant trade-offs that require careful consideration. Given these options, the heap-based approach stands out as the most balanced strategy for this problem. By using a max heap of size k, we can efficiently maintain the k closest points without sorting the entire list. This makes it particularly effective when k is much smaller than the total number of points, as it avoids the computational overhead of the brute force approach. At the same time, it offers more consistent performance compared to quick select, which can suffer from poor pivot selection in the worst case. The heap-based approach is also easier to implement than quick select, making it a practical choice for most scenarios. While it does require additional memory for the heap, this is manageable since the heap size is limited to k, and the trade-off in terms of consistency and simplicity is often worth it. In conclusion, the heap-based approach strikes the right balance between efficiency, simplicity, and reliability, making it our preferred solution for finding the k closest points to the origin. To solve the problem of finding the k closest points to the origin, we start by defining the task clearly. You are given a set of points in a 2D plane, each represented as x, y coordinates. The goal is to identify the k points that are closest to the origin, which is located at 0, 0. To measure closeness, we use the Euclidean distance formula. However, instead of computing the actual distance, which involves a square root operation, we can simply compare squared distances. This avoids unnecessary computational overhead. Now, the brute force approach begins by taking the input list of points and an integer k. First, we ensure k is valid, for example, it cannot exceed the number of points available. Next, we calculate the squared Euclidean distance for each point using the formula x squared plus y squared. These distances are then paired with their respective points and stored as tuples in a list. This step ensures we can easily manage both the distances and the points together for further processing. Once we have the list of distances paired with their respective points, the next step is to sort this list in ascending order based on the distances. Sorting ensures that the closest points appear at the beginning of the list. Python's built-in sorting algorithms, such as timsort, provide an efficient way to handle this, operating in O(n log n) time. After sorting, we can simply extract the first k elements from the sorted list, as these correspond to the k smallest distances. We only need the points from these tuples, so we discard the distance values and retain the point coordinates. This gives us the list of the k closest points to the origin. Finally, this result is returned as the output. By following these steps, we can solve the problem in a straightforward manner while keeping the implementation simple and intuitive. Additionally, the use of squared distances avoids unnecessary calculations, which helps improve the efficiency of the approach. Sorting the distance list ensures that the k smallest distances are at the start, making it easy to retrieve the closest points. However, there are some edge cases to consider. For example, if k is 0, the output should be an empty list since no points are requested. If k equals the total number of points, we return all points sorted by their distance to the origin. Another scenario involves ties. If multiple points have the same distance to the origin, the algorithm will include them based on their order in the sorted list. This behavior is consistent and deterministic. Looking at the data structures involved, the input list of points is iterated over to compute distances, which is an O(n) operation. Then, we use a list of tuples to pair points with their distances, which simplifies the process of sorting and extraction. These structures help keep the implementation both clear and efficient. Let's analyze the algorithm's complexity. Calculating the distance for all points involves iterating through the input list once, which is O(n). Sorting the list of distances requires O(n) log n, as sorting dominates the time complexity. Extracting the first k points from the sorted list is an O(k) operation, but this is negligible compared to sorting. Thus, the overall time complexity is O(n) log n. For space complexity, we need O(n) to store the distance list, as each point is paired with its distance. The final result list requires O(k) space to store the k closest points. Therefore, the overall space complexity is O(n). To optimize further, especially for very large datasets, we can use a max heap of size k. This allows us to maintain only the k smallest distances during the computation, reducing the sorting step to O(n) log k. This heap-based approach is particularly useful when the input size is extremely large, as it avoids sorting the entire list of distances. Let's walk through an example to see the algorithm in action. Suppose the input points are 1, 3, 3, 4, 2, -1, and k is 2. First, we calculate the squared distances for each point. 4, 1, 3, the distance is 1 squared plus 3 squared, which equals 10. 4, 3, 4, the distance is 3 squared plus 4 squared, which equals 25. For 2, -1, the distance is 2 squared plus -1 caret 2, which equals 5. These distances are stored as tuples, resulting in the list 10, 1, 3, 25, 3, 4, 5, 2, -1. Next, we sort this list by distance, giving us 5, 2, -1, 10, 1, 3, 25, 3, 4. We then select the first k equals 2 points from the sorted list, which are 2, -1, and 1, 3. The output is 2, -1, 1, 3. This example demonstrates how the algorithm efficiently identifies the k closest points to the origin. This implementation solves the k closest points to origin problem efficiently using a max heap. The class solution contains the method kClosest, which takes two arguments, points, a list of 2D points, and k, the number of closest points to find. To solve the problem, we use the heap library to maintain a max heap of size k. A max heap is used to efficiently track the k smallest distances. The squared distance of each point from the origin is calculated as x squared plus y squared. Squared distances are sufficient because square root computation is not needed for comparison. The algorithm iterates over each point, x, y, in the input list. If the size of the heap is less than k, the point is added to the heap. Otherwise, if the heap already contains k elements, the current point is added and the farthest point is removed using heap.heapishpop. This ensures that the heap always contains the k closest points. Finally, the k closest points are extracted from the heap and returned as a list of x, y coordinates. By maintaining the heap at size k, the solution achieves an efficient time complexity of O(n) log k, where n is the number of input points and k is the heap size. This implementation handles edge cases such as very small or large values of k and works for any valid input of points. Here, we start by importing the necessary utilities and defining our solution class. The main method, kClosest, takes in a 2D array of points and an integer k, representing the number of closest points we need to find. To achieve this, we use a priority queue, implemented as a max heap, to store the k closest points based on their distance from the origin. The comparator in the priority queue is set up to sort points by their squared distance in descending order, ensuring that the farthest point in the heap can be efficiently removed. We then iterate through each point in the input array. For every point, we add it to the heap using the offer method. If the heap size exceeds k, we remove the farthest point using poll, which ensures that the heap always contains only the k closest points. This process ensures that our heap dynamically maintains the required size while processing all points. Once all points have been processed, we extract the k closest points from the heap into a result array. We initialize an index to track the position in the result array, and while the heap is not empty, we pull points out of the heap and store them in the result array in order. Finally, we return the result array, which contains the k closest points to the origin. Additionally, there's a helper method called distance, which calculates the squared distance of a point from the origin. This method avoids the computational overhead of using square root, as we only need relative distances to compare points. By combining the heap logic with this squared distance calculation, the solution is both efficient and straightforward, making it a great use of priority queues for solving this problem. To solve the problem of finding the k closest points to the origin, let's start with an example where the input points are 1, 3, 2, 2, 2, minus 2, and k is 2. First, we initialize an empty max heap, which will help us keep track of the closest points. Next, we iterate through each point in the input. For the first point, 1, 3, we calculate its squared distance from the origin as dash 1 superscript 2 plus 3 superscript 2, which equals minus 10. Since the heap currently has fewer than k elements, we push this point into the heap. The updated heap now contains minus 10, 1, 3. Moving on to the second point, minus 2, 2, we compute its squared distance as dash minus 2 superscript 2 plus 2 superscript 2, which equals minus 8. Again, the heap size is less than k, so we add this point to the heap. The heap is now minus 10, 1, 3, minus 8, minus 2, 2. Next, we process the third point, 2, minus 2. Its squared distance is calculated as dash 2 superscript 2 plus minus 2 superscript 2, which equals minus 8. At this point, the heap is full with 2 elements, so we apply the heapishpop operation. This operation ensures that only the k closest points remain in the heap by replacing the farthest point, which has the smallest negative distance. Here, the point with distance minus 10 is replaced with 2 minus 2, as its distance of minus 8 is closer to the origin. The updated heap now contains minus 8, minus 2, 2, minus 8, 2, minus 2. Finally, we extract the k closest points from the heap, which gives us dash 2, 2, 2, minus 2. Note that the order of the output points may vary depending on the heap implementation. In another example, we are given the points 0, 1, 1, 0, 2, 2, and k is 1. After initializing an empty max heap, we begin iterating through the points. For the first point, 0, 1, we calculate its squared distance as dash 0 superscript 2 plus 1 superscript 2, which equals minus 1. Since the heap size is currently less than k, we push this point into the heap. The heap now contains minus 1, 0, 1. For the second point, 1, 0, the squared distance is also minus 1. Because the heap is at capacity, we perform a heapishpop operation. However, since the distance of 1, 0 is equal to minus 1, which is already present in the heap remains unchanged. The heap still contains minus 1, 0, 1. For the third point, 2, 2, we calculate its squared distance as dash 2 superscript 2 plus 2 superscript 2, which equals minus 8. Since this distance is farther from the origin than the current points in the heap, no replacement occurs. The heap remains minus 1, 0, 1. After iterating through all the points, we extract the k closest points from the heap. The result is 0, 1, which is the closest point to the origin in this case. Now, for a third example, we have the points 3, 3, 5, minus 1, dash 2, 4, with k set to 2. We initialize the max heap as usual and begin processing the points. For the first point, 3, 3, its squared distance is calculated as dash 3 superscript 2 plus 3 superscript 2, which equals minus 18. Since the heap size is less than k, we add this point to the heap. The heap now contains minus 18, 3, 3. For the second point, 5, minus 1, the squared distance is dash 5 superscript 2 plus minus 1 superscript 2, which equals minus 26. The heap is still not full, so we push this point into the heap. The heap is updated to minus 26, 5, minus 1, minus 18, 3, 3. Finally, we process the third point, minus 2, 4. Its squared distance is calculated as dash minus 2 superscript 2 plus 4 superscript 2, which equals minus 20. Since the heap is full, we perform a heapishpop operation. This replaces the farthest point, which has the smallest negative distance, minus 26, with the new point, minus 2, 4. The updated heap now contains -20, -2, 4, -18, 3, 3. After extracting the k closest points from the heap, the result is -2, 4, 3, 3. From these examples, we can derive some key insights. First, the heap stores negative distances because Python's heap is a min heap by default, and we need to simulate a max heap. Second, maintaining the heap size at k ensures that we only store the closest points, optimizing both space and time complexity. The overall complexity of the algorithm is O, n log k, where n is the number of points. Here, we analyze the time complexity of the algorithm step by step. First, the algorithm uses a max heap to maintain the k closest points. Operations on the heap, such as inserting or replacing elements, have a time complexity of O log k, because the heap contains at most k elements. Next, the algorithm iterates through all in points in the input list. For each point, it calculates the squared distance from the origin, which is an O(1) operation since it's just a basic arithmetic computation. After calculating the distance, it performs a heap operation, either adding a new point or replacing the farthest point in the heap. Each heap operation costs O log k. Finally, to build the result, the algorithm extracts k elements from the heap, which requires O, k, time. These three steps form the foundation of the time complexity analysis. Now, when we combine these steps, iterating through endpoints and performing a heap operation for each gives us O, n asterisk log k. Extracting the k closest points from the heap adds O, k, to the total. However, O, k, is much smaller compared to O, n asterisk log k, when n is large, so it doesn't affect the overall complexity. Therefore, the time complexity of the algorithm is O, n asterisk log k. For the space complexity, the main contributor is the max heap, which stores at most k elements. Each element in the heap consists of three values, the squared distance and the two coordinates of the point. This requires O, k, space. The input list, which contains n points, doesn't count towards additional space usage since it's part of the input. These factors determine the space requirements of the algorithm. In addition to the heap, we must also consider the output storage. The output consists of k points, where each point is represented as a list of two integers. This requires O, k, space, as we are simply storing the k closest points. When we combine the space used by the heap and the space used for the output, the total space complexity becomes O, k. Importantly, there are no other significant data structures or additional memory allocations in the algorithm. Therefore, the overall space complexity is determined entirely by the heap size and the output size, both of which are proportional to k. To put this into perspective, let's compare this optimized approach to a brute force method. In the brute force approach, we would calculate the squared distances for all n points, which takes O, n, time, and then sort the points by distance, which adds O, n asterisk log n. Extracting the first k points from the sorted list would take O, k, time, making the total time complexity O, n asterisk log n. The space complexity in the brute force method is O, n, as we need to store the entire sorted list of points. On the other hand, the optimized algorithm avoids sorting all n points by maintaining only the k closest points in a max heap. This reduces the time complexity to O, n asterisk log k, and the space complexity to O, k. These improvements make the optimized algorithm more efficient, particularly when k is much smaller than n. Finally, let's break down the algorithm's performance in different cases. In the best case, where k is very small compared to n, such as k equals 1, the algorithm still has a time complexity of O, n asterisk log k, but the constant factors involved are minimal, making it very efficient. In the average case, where k is a moderate fraction of n, the time complexity remains O, n asterisk log k, which is manageable for most practical scenarios. In the worst case, where k is close to n, the time complexity approaches O, n asterisk log n, as the heap essentially grows to accommodate almost all the points. Despite this, it is still faster than the brute force approach, which sorts the entire list. To summarize, the time complexity is consistently O, n asterisk log k, and the space complexity is O, k, regardless of the case. This makes the algorithm robust and scalable for a wide range of input sizes. When solving this problem, there are some common mistakes to watch out for. First, not handling edge cases for k can cause issues. If k is 0 or greater than the total number of points, algorithms might fail or behave unpredictably. It's important to validate k before starting any computations to ensure your solution handles these scenarios gracefully. Another mistake is sorting all the points when you only need the top k closest ones. Full sorting has a time complexity of n log n, which is inefficient compared to methods like partial sorting or using a heap, which can achieve n log k. Incorrect distance calculations are another pitfall. Using the Euclidean distance formula with a square root is unnecessary, as comparing squared distances is sufficient and avoids the computational overhead of square root operations. Lastly, overlooking negative coordinates is a common issue. Some implementations assume all points are in the first quadrant, which leads to errors when working with points in other quadrants. Always account for negative coordinates to ensure accurate calculations. Another frequent mistake is choosing the wrong data structure. For example, using a max heap instead of a min heap, or vice versa, can make managing the k closest points unnecessarily complex. The type of heap you use should align with whether you're tracking the smallest or largest elements. Now, when discussing your solution in an interview, it's crucial to highlight trade-offs between different approaches. For instance, brute force methods like sorting are simple but inefficient, while heap-based methods offer better performance for large inputs. Be prepared to discuss edge cases, such as when k is 0, when k exceeds the number of points, or when multiple points overlap at the origin. Interviewers often value computational efficiency, so emphasize why your solution is optimized, like using a heap for n log k, instead of n log n sorting. Using real-world analogies, such as comparing this problem to finding the closest facilities to a location, can also help clarify your thought process. Finally, adaptability is key. If the interviewer modifies the problem, for example, asking for the farthest points instead of the closest, demonstrate how your approach can be adjusted and explain the rationale behind those changes. This problem is closely related to other algorithmic challenges, so practicing those can help reinforce your understanding. For instance, the problem itself, k closest points to origin, is a great starting point for exploring various methods like sorting, heaps, and divide and conquer. The kth largest element in an array problem is another valuable exercise, as it uses a similar heap-based approach to efficiently find the kth largest or smallest element. Minimum cost to connect sticks is another heap-based problem that focuses on optimization, making it useful for honing your skills with priority queues. Lastly, top k frequent elements emphasizes efficient techniques for finding top elements, like heaps or bucket sort, which are relevant to solving the current problem. Exploring these related problems will help you build a strong foundation for tackling variations of this question. When it comes to alternative approaches, there are several strategies to consider, each with its own trade-offs. The brute force method involves sorting all the points, which has a time complexity of n log n. While simple to implement, this approach is inefficient for large inputs when we only need the top k results. A heap-based approach, on the other hand, is much more efficient, with a time complexity of n log k. By maintaining a heap of size k, you can efficiently track the closest points. However, managing the heap requires careful implementation to ensure correctness. Another option is the divide and conquer method, such as quick select, which has an average time complexity of n, but can degrade to n squared, in the worst case without optimizations like randomization. Finally, a grid or bucket-based approach can be useful for problems with geometric constraints, especially when the space is bounded. However, this method is less generalizable and may not apply to all variations of the problem. Each approach has its strengths, so the best choice will depend on the problem's specific requirements and constraints. Great job! We've wrapped up the discussion on k closest points to origin. Remember the importance of choosing the right approach based on time and space complexity. Keep practicing similar problems to strengthen your skills. Thank you for watching, and see you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!